Swayam Prabha. Digital India. Educated India.
Okay. I expected a question from you, that is, what happens during synthesis of an ester from a simple alcohol and a simple acid, and synthesis of a polyester from a dialcohol and a diacid. I mentioned that this polyesterification reaction occurs in large number of intermediate steps involving many intermediates. That means, I wanted to know from you, is there any, this question, is there any influence of is there influence of size of the reactive intermediates on the polymerization kinetics? Then what is that influence?
Sir, as molecular weight increases step by step, then
Yes.
random velocity decreases. That's why number of collision also decreases.
Then ultimately what will happen? Reactivity of the intermediates will gradually decrease. Then one cannot expect a very high molecular weight. That is not the situation. No, no sir, you are wrong. Please deliberate on this point after the class in your hostel or anywhere among you. Is there any influence of the size of the intermediates on the reactivity of the functional groups of intermediates? When it starts, there are functional groups of carboxyl and hydroxyl, they are reactive to each other. So, as that intermediate length, that means the distance between two carboxyl and hydroxyl groups, one carboxyl and hydroxyl groups increases, then whether the reactivity of the end groups will remain same or change, that is the question. That is the question.
Reactivity of in group is not changing, but
that you have to ensure. You can say, I can say, but it is to be proved. It is to be proved. So, I am giving you a clue. You go through this audience book, there are some results and data given using some compounds of homologous series of gradually higher molecular weight. Okay, you see the result there. Whatever it may be, you look into all sorts of those possibilities and get the thing clarified. I want a clear answer from you in the next class. Okay. Now, please look into the equation, right? The self catalyzed polyesterification. very simple kinetics. Overall rate minus sign, you know the sense of meaning of the minus sign here, since it is depletion. So, here in this rate equation, second power to the carboxyl group is given and first power to the hydroxyl group is given. So, it is overall third order reaction. Why this second power to the carboxyl group? Because one of the acid molecule is involved in reaction mid as a catalyst, self catalyzed. That is why this is second power and first power, overall third order reaction. A very simple thing in terms of replacing in terms of monomer concentration, we get this is the relation. Then applying initial and boundary conditions at t is equal to 0, m becomes m0, and to remove that integration constant, we apply initial and boundary conditions, simple mathematics, you know, and ultimately we come to this final form of this rate equation, twice monomer concentration square of the monomer, initial concentration of the monomer into rate constant into T divided by square of the degree of polymerization dP minus 1. Okay. This is the rate equation for form of the rate equation after in case of self catalyzed polyesterification or polycondensation reaction. I should say polycondensation, it may be true for the same for polyamidification also. Clear? I am going to the next one.
So, second order with respect to carboxyl.
Because one of the acid molecule is involved in catalyzing the esterification reaction. It is not given back because it is consumed. So, its concentration is included in the rate expression. Since acid molecule is involved in the reactant acid molecule is involved in catalyzing the polyesterification reaction. So, its concentration is involved in the rate expression. So, that is why it is second power to the carboxyl group. I am going to the next one. Look at the growth, polymer growth. Now, this y axis, this is schematic, actually we cannot show here actual data due to copyright problem. So, here you see this is the square of the degree of polymerization, number of average degree of polymerization versus time. So, it shows actually it is not linear overall, although I have shown overall linear for simplicity and clarity. You please go through the books I have referred, there you will find some deviation from linearity for so and different many different regions which are obvious from these rate expressions I have shown in the mechanism of polyesterification involving acid, carboxyl group, etc., different rate constants. So, all those are involved there. So, if you want to know those who are interested, they can see audience book for detail. Okay. Now, here you see if it is linear, then this is square of the degree of polymerization, and this axis shows percent reaction, and this is the degree of polymerization. So, here it is 400, so it is 20. So, up to say 1800, say 1600, 1700 minute time, only a dP of 20 could be achieved, or less than that, very small. So, reaction is very slow. This indicates the polymerization reaction, polyesterification reaction using self catalyzed reaction, following self catalyzed reaction, this polymerization is slow. Yes, please, you are you following these things? Okay, electronics, following? Okay. So, this is, here is a proof that self catalyzed polyesterification reaction or esterification reaction is a slow process. So, the productivity of the polymer, if you want to go for industrial manufacture of a polyester without using any external catalyst, so it will take large time, productivity will be less, the cost of the product will be very high. Where you see, this is related to the first power of time, square is related to the first power of time. So, the degree of polymerization is the growth is very slow. This indicates growth is very slow. So, this thing I have already explained in the previous curve, showing the previous curve. Then externally catalyzed polyesterification, the same kind of red expression, where you see this concentration of either carboxyl or carboxyl involving carboxyl and hydroxyl both, but since some external acid is used as a catalyst, the concentration of acid is not involved in this rate expression, it is not included here. So, it is square. So, this rate is second order reaction, this is a second order reaction, first order on each of the functional groups, either acid or alcohol, and applying initial and boundary conditions, ultimately you can get degree of polymerization equal to 1 plus m0 k prime t. Here you see degree of polymerization is directly related to T. With the increase in time, there will be growth of molecular size, xn bar. Okay. Look at this curve. There you saw that for a growth of a dP of 18 only, 18 to 20, it needed say 1600 minute time. Here you see within 800 minutes, half a time, you can get much higher growth. Say dP is around say 90 or 95, like that. So, this external use of external catalyst increases the polymer production rate, polymer synthesis rate. So, in a small time, in a less time, you can produce huge quantity of polymer. So, this process is faster if you use an external acid as a catalyst. So, catalyzed polyesterification, catalyzed polyamidification reaction, or any condensation reaction, if that needs a catalyst, it is better to use the catalyst in order to augment the polymerization, in order to increase the productivity. Not only that, the reaction condition also, reaction conditions will be mild, otherwise you have to use harsh reaction conditions, harsh polymerization conditions. So, these considerations are there. As before, it explains that this degree of polymerization is related to the first power of this time. Now, I am showing these relations. You can go for, you should go for numerical calculations. You will find that how much time is required for a synthesis of a polymer from its starting point. You can theoretically calculate with the help of this Carruthers equation and this reaction kinetics. If you know the value of course this is known, initial concentration is known, rate constant you have to evaluate by some other experiment. So, if you know the rate constant, polymerization rate constant, if you know the initial concentration, then in order to get a dP, suppose you want to manufacture a polymer, say degree of polymerization 1000, then how much time is required for that achieving that 1000 dP, degree of polymerization, you can easily calculate. Suppose you are employed in a polymer manufacturing unit, your boss has told you, make a project, make a time calculation that how much time will be required to produce say 1000 metric ton of this polymer product, then you have to calculate. How do you calculate? You have to follow this thing, you have to follow this principle, follow this process, you can easily calculate. For that you have to find out the data of this rate constant for that particular polyesterification reaction, then you can easily calculate. Okay. Then there are certain limiting situations, as I have told, molecular rate of polymer and its control, degree of polymerization and extent of reaction, we know all these things. Carruthers equation is this 1 by 1 minus p, simplest form of Carruthers equation. Please do not forget, this is related to this relates parameters of degree of polymerization and extent of reaction involving bifunctional monomers and in stoichiometric ratio, in stoichiometric amounts. In stoichiometric amounts meaning that reactants are used in 1:1 molar ratio, equivalent molar ratio, same molar ratio. Okay. Please do not confuse, because there are certain things will be coming later, those will be sufficient for you to confuse yourself. That is why I am telling you, please do not forget that xn bar equal to 1 by 1 minus p, the simplest form of Carruthers equation involving bifunctional monomers, strictly bifunctional monomers, and strict control of stoichiometry between the reactants, and if that is the 1 by 1 minus p, provided the extent of reaction is p. Okay. From that you can calculate the molecular weight, calculate the degree of polymerization. And you know the limiting situation, I have already told how it becomes infinity, infinite molecular weight. In this juncture, let me tell you one corollary, that is, suppose you have taken natural rubber, I told you this is thermoplastic material, dry natural rubber is thermoplastic material, but when the dry natural rubber is mixed with sulfur and other functional compounds, functional additives, it forms a mass which is reactive. Then after application of heat and pressure, it converts to a thermoset product known as vulcanized rubber. So, when you started with the molecular weight of natural rubber was say 5 lakh, suppose, after vulcanization what will be the molecular weight of the vulcanized product? Will it remain at 5 lakh, or will it increase to 10 lakh, or will it decrease lower than 5 lakh? Increase to what value?
Depending on the amount of sulfur you have, or the amount of crushing.
Will it be, suppose he has used 2%, you have used 5%. So, in case of 2%, what will be the molecular weight? In case of 5% sulfur, what will be the molecular weight? If it is 30%, what will be the molecular weight? If it is 20%, what will be the molecular weight? Are those will be different or same or different? If it is different, how much different? This is a question. Keep this question as homework assignment. Next day come with us, submit me the assignment. I am not giving very huge assignments. So, one question I gave is the second question, what will be the molecular weight of vulcanized rubber after it is converted from thermoplastic to thermoset. Next, now let us see the music. If we move beyond stoichiometry, if we disturb the stoichiometry, of course that is the reality, because while taking the weights of the reactants, we cannot take the weights perfectly, because I have a 4 place of decimal balance, you have a 2 place of decimal balance, you have a very crude balance that cannot make a difference between 5 gram, whereas my balance can make a difference between 5 milligram. So, you are taking weight in your balance, I am taking weight in my balance, and that will cause a large change in the nature of the reaction. That is non-stoichiometry. So, polymerization of, you consider, in order to evaluate in that non-stoichiometric situation what can happen, how to assess, how to evaluate the situation, how to monitor the situation, we have to see. So, non-stoichiometry means that non-stoichiometry may arise out of wrong taking of weights, or it may contain certain impurities. If we know from the label of the container that the reactant is 98% pure, so 2% impurity is there. So, you have to include that impurity in your calculation. So, instead of say 5 kg weight, you have to take probably 5.2 kg weight, including that impurity into consideration, like this. So, you have to know what is the impurity level there. Then you have to know what is the balance, what is the sensitivity of the balance, that you have to also include. Correction factor. Okay. You cannot ignore. If you ignore, you will not get a polymer. So, in a case of polymerization of two monomers having A functional groups and B functional groups, both are bifunctional, A and B type. Now, in that case, suppose by mistake one monomer is taken in little excess, say BB is taken in little excess, what will be the situation? Let us see. Number of A functional groups are Na, designated as Na, number of B functional groups designated as NB. Then total number of functional groups, A functional groups will be 2 into A, number of molecules into 2, because each molecule is bifunctional. So, NB is equal to 2 into BB. So, the stoichiometric imbalance then, if you take a little excess of B, so that stoichiometric imbalance is expressed with the help of a parameter R is equal to Na by Nb, and this R cannot be greater than unity, it should be less than unity or less than or equal to unity. Okay. If it is less than unity, then Nb is in excess. So, that way let us see. So, total number of monomer molecules then Na plus Nb by 2, this is a very simple thing, or Na into 1 plus in terms of R. If you replace this Nb Na in terms of only one particular functional group, A functional groups, 1 plus 1 bar plus 1 by R whole divided by 2 number of functional groups presents. Then extent of reaction, we introduce this parameter extent of reaction P. Extent of reaction P is equal to the fraction of A groups that has reacted at a particular time. extended prime T. So, the fraction of B groups that have reacted will be Rp. So, fraction of unreacted A groups 1 minus P, fraction of unreacted B groups 1 minus Rp, and total number of unreacted A groups will be Na into 1 minus P, total number of unreacted B groups will be Nb into 1 minus Rp. Very simple calculation, simple derivation. So, why you are doing these things? Because we have to calculate the value of degree of polymerization, number average degree of polymerization or molecular weight, because you know number of average degree of polymerization is equal to N0 by N, number of molecules initially present divided by number of molecules present at any time t. So, number of molecules initially present and number of molecules present at any time t, for those two parameters, this process we are following for calculation. Okay. So, total number of polymer chain ends then will be, because these are the Na functional groups and Nb functional groups. Now, you have got the concept that polymer molecules will have some end groups in the form of A or B groups. So, if the ends, number of ends are having A or B, so total number of chain ends will be this number of polymer chain ends. Suppose a system contains so many polymer molecules of this size. So, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 species are there, and each species has 2 ends. So, total number of ends 10 into 2, 20 from that logic. So, total number of polymer chain ends, then if we know the total number of polymer chain ends, we can experimentally evaluate, we can experimentally determine that thing, we can experimentally determine how many end groups are there this side and this side by tachymetric estimation or by some other spectroscopic technique. Okay. So, total number of ends we can calculate, then total number of polymer molecules, divided this number, total number of end groups by 2, you will get number of polymer molecules. Then you substitute those values here, xn bar is equal to number initially present, number present at any time t. So, from there you have already seen Na into 1 plus 1 by R. Okay. Ultimately, this leads to 1 plus R divided by 1 plus R minus twice Rp. So, this is a relation involving stoichiometric imbalance R and extent of reaction P, where you have used bifunctional monomers in which one of the monomers are taken in excess, or there are certain impurity materials, those impurity materials are counted as some functional groups or something like that. There are various other considerations. If you go through that audience book, you will get those details, but for all of you it is not necessary. Those who are interested, you are referred to that book for details of informations there. But if you are intelligent enough, looking at this relation, you can evaluate, you can derive many things. Now, here limiting situations might be R may be equal to 1, that means Na can be equal to Nb, perfect stoichiometry. In that case, for R is equal to 1 means Na is equal to Nb, Xn bar is equal to 1 plus 1 divided by 1 plus 1 minus 2p. So, for equimolar quantities of reactants, the Carruthers equation is 1 by 1 minus p, and when p is equal to 1, but Na is not equal to Nb, then Xn bar is equal to 1 plus R divided by 1 plus 1 plus R minus twice R. So, it will be equal to 1 plus R divided by 1 minus R. So, even if you continue up to 10% reaction, the degree of polymerization is equal to 1 plus R by 1 minus R. Now, here this value of R, you can have several situations, you can test, take again this as your homework assignment for different values of R, 0.98, 0.97, 0.9, 0.99 like this, then what will be the value of degree of polymerization? That means, if one of the reactant is used a 0.1 mole percent excess or 0.5 mole percent excess or 1 mole percent excess, then what happens to this degree of polymerization? You will get that value. Am I clear? There will be numerical calculations. So, please have a practice in the evening hours for different values of this is one case. Another case, when both P and R varies, different P and different R, what can happen? It is very difficult to achieve 100% reaction. That will take very long time. So, before that you have to stop the polymerization. In that case, if again there is some mistake in R, then we may not get a polymer product. So, what is that situation? You have to theoretically achieve. Or if there is any problem in polymer manufacture in your industry, you find molecularity is very low, your quality control department has given you a feedback, the product charge, your feed charge, you have charged to the reactor, with that feed charge, this is the product, this is the molecular weight, then the entire responsibility lies on you to find out the fault, where is the fault, where lies the fault. So, you have to go for calculation. So, for this thing, this calculation is necessary. Okay. I have already told you limiting forms of this Carruthers equation. Again, this is a schematic diagram. This is drawn by me only for convincing you. Now, y axis you see, this shows degree of number average degree of polymerization. X axis shows three different axes, the different situations. In one case, you see the font is little smaller, I could not accommodate. Mole percent excess BB, that means degree of polymerization changes with excess B groups, 1 mole percent, 2 mole percent, 3 mole percent, 4 mole percent. You see, in one particular case, you see how this extent of reaction changes. So, with the change in extent of reaction and along with this stoichiometry, what is the molecular rate? Here you see, you can have very high molecular rate provided you continue the reaction up to 10% conversion, then only you have to take very small amount of the B groups in excess. As you go increasing the B groups, then you will end up with molecular weight, say dP 50 or even less than 50. You understand? Try to give some time on this schematic diagram. This diagram utilizes extent of reaction and one of the monomers in excess. Okay. If you go on increasing the concentration of the monomer, excess monomer, then you have to compromise with the degree of polymerization, provided even if you carry out the reaction to 10% completion. Do you understand? A top curve, look at the top curve. Suppose you are satisfied with your end group analysis that you have carried the polymerization reaction to completion because you have achieved P is equal to 1, but your product molecularity is very less. Your diagnosis will be, locating the fault will be in this impurity or during weighing. That means probably you have taken one of the monomers in large excess. So either 2 mole percent you have taken excess, if you are, here is the dP less than 100, so probably you have definitely have taken 2 mole percent excess of monomer B. Okay. So other cases mole percent excess of B for N is equal to NB, this is another case, and stoichiometric ratio R, if it is expressed in this way, 1 perfect stoichiometry, R is equal to 1, Na is equal to Nb, then deviating from the stoichiometry to lower values, R value 0.96, and you see the degree of polymerization.
Second case, mole percentage excess of B for Na is equal to
Mole percent excess B. You see, here you can add some monofunctional compound. It signifies that you have started with AA and BB, both are bifunctional. Now, how to control the molecular rate? Suppose those groups are very reactive, then you have to stop the polymerization. You can stop it chemically by adding a monofunctional compound. Suppose you have taken, say, ethylene glycol and adipic acid. If you want to stop the polymerization, you can add little formic acid or acetic acid. In that case, mole percent excess of B only, even if you have taken Na is equal to Nb, even if you have taken Na is equal to Nb, then you can control the polymerization by taking a monofunctional reagent, that may be acetic acid or formic acid or a methanol or ethanol.
Na is equal to NB means in the sense we are taking equal stoichiometry.
Stoichiometry of the monomers AA and BB. Suppose you have taken ethylene glycol and adipic acid. Those are monomers to take part in polymerization. Okay.
Of equal stoichiometry.
Equal stoichiometry. For that case, you can have a situation that you have to control the molecular weight, you have to limit the molecular weight, not a dP of say 1000. You do not want a dP of 1000, you want a dP of say 100 for certain purpose. It is necessary. It is necessary. It is not always true that you have to lead to molecular polymer of highest molecular weight? Not necessarily. That depends on the properties you want. You may use that product in some painting for your surface coating purpose, for making a film. In that case, you need a low molecular weight product, whereas for mechanical application, for load bearing application, you may need a very high molecular weight product. Those things I have not explained, structure property relations. First of all, let me complete this synthesis principles of synthesis part, then I shall discuss those things, then it will be clarified. So, here it is a very good question you have asked, that what is the necessity of this thing? Mole percent excess B means you have to stop the polymerization using a monofunctional reagent having B functional group. Am I clear? Is it clear? Okay. This diagram is very informative, because you can calculate the amount of reactants for synthesizing any polymer, as well as you can know how much time should be continued for this polymer growth, how much time should be allowed for getting a suitable quantity of polymer as well as desired molecular weight level. So, you please do some numerical calculations taking different ratios of the reactants, that means R value, or you can use one of the reactant in little excess, or you can use, here you see, you can use some monofunctional reactant also. Monofunctional reactant, I mean that if you take say adipic acid and ethylene glycol for getting polyethylene terephthalate PET polymer, in order to stop the polymerization at any stage, you can either add to the reactor a monofunctional compound like say acetic acid or methanol or ethanol. So, that way, by adding some monofunctional compound at one time, say after 5 hours or 2 hours like that, then you can know how much will be the molecular weight. Or if you want a specific molecular weight, then you can find out the time required for that growth as well as how much amount of monofunctional reactant is to be added at what time. So, that will stop the polymerization. Now, let us pass on to multi-chain polymerization. What do you mean by multi-chain polymerization? As you have seen that the minimum requirement of polymerizability of these monomers lies in the ratio of the two reactants as well as the bifunctionality of the monomers. Strict control of bifunctionality as well as strict control of stoichiometry, molar ratio of the reactants leads to a linear polymer structure, linear chain polymer. Now, if there is certain impurity, that impurity can affect the molecular structure of the polymer. It may not be linear, it may be branched, or it may be even cross-linked. Now, there are certain polymerization reactions or certain polymers where we deliberately use a bifunctional monomer with a trifunctional monomer. Say, you can react phthalic anhydride or phthalic acid, phthalic anhydride and glycerol. Now, this is phthalic anhydride is a bifunctional, F is equal to 2, here F is equal to 3. What will happen? Now, in case of exclusively bifunctional monomers, you will get a linear polymer chain. From exclusively exclusively bifunctional monomer. Okay. But if you take some quantity of a trifunctional monomer along with this bifunctional monomer having the same kind of functional groups, then you can get a branched polymer. How it happens? How it happens? Say, suppose you want to synthesize a polymer taking a bifunctional monomer having functional groups B. Then you take a trifunctional monomer like this having functional groups A. 3 functional groups are there. So, you can get a polymer from this like I am sorry, B A B B, then it may again link to A B B like this. Here it will continue. So on and so forth. Do you understand? So, this way you can, there is a possibility of formation of branch. Beyond that, it can lead to a cross-linked 3-dimensional network system of polymer, 3-dimensional network polymer. That thing we will discuss today. Now, this multi-chain polymerization, where the polymerization involving a bifunctional monomer of one kind and a trifunctional monomer of other kind. For calculation of degree of polymerization, concept of average functionality should be introduced. Otherwise, how we can calculate? So, here this functional, in case of bifunctional monomers, functionality is 2, F is equal to 2. Now, if we take a mixture of bifunctional monomer with a trifunctional monomer like 1 mole of or 2 mole of say bifunctional monomer, I am sorry, 2 mole of bifunctional monomer with 3 moles of say trifunctional monomer, or 3 moles of bifunctional monomer plus 2 moles of trifunctional monomer. Let us see what happens. Now, here in this case F is equal to 2, say F1 is equal to 2 and F2 is equal to 3 for this one. F1 is equal to 2, F2 is equal to 3. Now, what is the average functionality? That average functionality can be calculated from this relation. How? Now, if you take 3 moles of this bifunctional monomer, 2 moles of this thing, so it will be 3 into 2 functional groups plus 2 into 3 functional groups. So, this equals 12. So, average functionality F average should be equal to 12 by how many moles? 5 moles. So, it is coming around 2.4. So, for this system average functionality F average is equal to 2.4. It is very simple. Once you calculate this thing, then you can calculate the extent of polymerization P. Average number of functional groups present in the system. I have shown this calculation. If you take a bifunctional monomer BB, where you have taken 3 moles of BB, so total number of functional groups is in this case 6, and trifunctional 2 moles of trifunctional monomer AAA. So, average number of functional groups here 2 into 3 6, total is 12. How many moles are there? 3 plus 2, 5 moles. So, what you have done, total number of functional groups present in the system divided by total number of moles of monomer you have taken. So, this is the average functionality, and that can be calculated with the help of this formula. So, then from this thing, with the taking the help of average functionality, we can calculate the extent of P, the extent of polymerization. Extent of polymerization, which is related to this average functionality, as well as this is related to the degree of polymerization, action bar. How? Now, from the definition of this extent of reaction, you see here, N0 is the initial number of moles present in the system, N is the number of moles reacted, so number of moles remaining is this. Total number of functional groups for each monomer, if it is a bifunctional, no, not that, for each event of reaction between 2 opposing functional groups, say one hydroxyl and one carboxyl group will react. So, this is the total number of functional groups reacted divided by functional groups present, that is the extent of reaction. The initial number of functional groups present, because this is the F average is the average functionality multiplied by the total number of moles present initially, then this is the moles present at any instant of time, moles of reactants present at any instant of time, functional groups. So, the ratio of these two is the extent of reaction. Any ambiguity, any doubt? Once again I am repeating, P is the amount of reaction occurred at any instant of time, that means number of functional groups that has reacted, or fraction of functional group that has reacted, or percent of reaction that has happened at any particular instant of time. To express this phenomena mathematically, we can see, we can define this way. So, this is the initial number of functional groups present, what we have taken by multiplying the average functionality F average by the original number of molecules, and this here N0 is the initial number of moles, N has reacted. So, remaining N0 minus N, since each event of reaction between a carboxyl and a hydroxyl group, 2 groups will be consumed, one hydroxyl and one carboxyl. So, this 2 factor has come, okay. So, this ratio is the extent of reaction. Now, on simple derivation, it comes to equal to 2 into xn bar minus 1 divided by xn bar F average. Xn bar is average number, average degree of polymerization, okay. So, on rearranging, we can get xn bar is equal to 2 by 2 minus P into F average, or P is equal to 2A by F average minus 2 by xn bar F average, okay. There is a chance, there is a chance of analyzing the situation. What will happen if the molecular weight or degree of polymerization becomes infinite? So, if xn bar value is infinite, then this term will vanish, will be 0. So, it will be 2 by f average. So, at the start of gelation, at the start of cross linking, once the cross linking reaction has started, intermolecular linkage between the molecules has started, entire system is gelled, means it is cross linked. So, last day I told you, if it gels or if it forms cross link structure, the molecular weight becomes infinite. So, at the incipient of gelation, at the moment of gelation, we consider that the entire system has been converted to a single molecule and its molecular weight is infinite. From that concept, this term vanishes and this Pc is the extent of reaction, critical extent of reaction. Pc becomes the critical extent of reaction, beyond which one should not continue the polymerization. If somebody continues, then your polymer mass will be a gel. You cannot apply that, you cannot process that, you cannot convert that product into a polymer into a suitable product like pen or a bucket or anything. You cannot, because that has converted to a gel, cross linked. That will be neither soluble in a solvent, nor you can melt it. If it is not soluble in a solvent, you cannot make any product, or if it is not meltable, you cannot make any product through processing using different machineries, say extruder machine or injection molding or any other machine, where it needs to be heated for increasing the flow by heating. Do you understand? So, it should be stopped below the gelations to start. Before it starts gelation, the polymerization should be stopped. So, that critical extent of reaction is Pc, which is equal to 2 by f average. Okay.
In the previous case you got
Thank you.